Okay, this is 8.2, linear systems in three variables. So the last section we did was linear systems of two variables, so two equations, two variables. So now we kind of upped it a little bit to have three. So let's try to visualize what a solution with three equations, three variables looks like. So that is in 3D, right? We have now x, y, and z. So we go out x, right? And then out y, and then up z. Okay, so it's kind of easiest if you look in the corner of a room, and then you can see kind of what's happening is that one of the kind of horizontal lines or corners is the x, one is the y, and the up corner is the z. So that kind of graph that we have here fits right into the corner of a room. So that can help you visualize a little bit. Okay, so now let's think about kind of what different types of solutions we can get from these systems. So again, this is kind of what it looks like first. So this is kind of what one solution can look like, and then kind of a version of multi-solutions, and then another version of multi-solutions, and then a no solution. So let's name them like we did. So this is, again, unique solution, and then linear dependence, okay, because right here, this is a line, right? And then this is the coincident dependence, all the same, okay? And then the no solutions, like we said. So the type of answer you'll get. The unique solution obviously just gives us a point. Then linear dependence gives us a line. Then the coincident dependence, that's the system that we were given, basically. That's the answer, okay? One of them kind of thing would be the answer. And then obviously no solutions. So let's go straight into an example here. If we have this system, so you can do any of the three ways that we learned last time in graphing or substitution or elimination, right? Now, a lot of times, just like kind of happened in the examples from the last section, a lot of times elimination is kind of easiest, but don't let that kind of streamline you. You can choose whatever way you want to use, okay? So now, having said that, this one kind of easily lends itself to elimination because right away we see we have negative 2z and 2z. We can right away cancel that out, right? So let's go ahead and do that. Now, we want to make sure to eliminate the z out of kind of all the equations and get 2. So every time you eliminate in a variable, you should kind of have one less equation as well. So we're going to also multiply this one by 2 as well, that third one. So that new equation, multiplying this by 2, will give us 2x plus 4y minus 2z is equal to 10. Okay, so first we're going to do, it's also good to number your equations. So this first one, and then the second one, and the third one, okay? And then this is just kind of also the third one, right? So we're going to take 1 and 2 here first and add them together. So that's these guys right here, right? So we have x plus y plus 2z is equal to negative 3, and 2x plus y minus 2z is equal to 4. So just add down. X and 2x is 3x, y and y is 2y, 2z minus 2z is 0z, minus 3 and 4 is 1. So that means now our kind of fourth equation is 3x plus 2y is equal to 1. So our next step is going to be to want to get rid of z out of this equation, right? So that means to easily do that, we want to use 1 and the second version of 3. So next is 1 and 3. So that's x plus y plus 2z is equal to negative 3, and 2x plus 4y minus 2z is equal to 10. So add down, and we have 3x plus 5y plus 0z is equal to 7, right? So now I'm going to write this equation down here so it's with 4. So that one's number 5, and we have 3x plus 5y is equal to 7. So let's go ahead and multiply one of these by a negative. Let's do the first one so that we don't end up with a negative y. Doesn't truly matter though. So we're going to multiply this one by negative 1. So we get kind of a new version of 4, and it is negative 3x minus 2y is equal to negative 1. So let's add those down, and we get 0x plus 3y is equal to 6. So this is kind of our 6th equation, is wrong color there, is 3y is equal to 6. So that means y is equal to 2. We have our first solution. So now we kind of work backwards, okay? We can go back to 4 and 5, right? Because we have 6 here. So we can use either 4 or 5 to plug in for y to find x. So let's take the first version of 4 because it has smaller numbers and it's all positive. That's always kind of nice. So we have 3x plus 2 times 2 equals 1. So then 3x plus 4 is equal to 1. So 3x equals negative 3. So x equals negative 1, right? So there's our second solution portion. Now let's find z. So that's going back up into one of the original 3 equations that we were given. So let's plug into the first one, just because again it's all positive and all small numbers for the coefficients. So we have negative 1 for x plus 2 for y plus 2z is equal to negative 3. So then we have this is 1 plus 2z is equal to negative 3. So then, sorry, I'm going to jump up here. We have to subtract the 1 over. So 2z is equal to negative 4. So then z is equal to negative 2. There's our third portion of the solution, right? So we just found our solution to be a triple pair, okay? Or a ordered triple, there we go, sorry. So our x value is negative 1, our y value is 2, and our z value is negative 2, okay? Now again, we can check that in, right, we just used that first equation, so we could check it in the second equation. So let me erase a little bit so that we have some room. I'll erase this part here. Takes a second. There we go. So if we plug into the second equation, we have 2 times x, which is negative 1, plus y, which is 2, minus 2z, which is negative 2. That's negative 2 plus 2 plus 4. Well, negative 2 plus 2 is 0, plus 4 is 4. That's that answer. So that one's good. Now let's plug it into the third equation, right? So we have x, which is negative 1, plus 2y, which is 2, minus z, which is negative 2. Negative 1 plus 2 and 2 is 4. Minus minus makes plus 2. Negative 1 plus 4 is 3. Plus 2 is 5, which is the answer to that equation. So this is the solution to this system. Okay, so it takes a little longer because now we have a whole extra equation with another variable, but it's the same steps, so just treat it that way. All right, so let's try it again. Notice this equation right here already doesn't have z, so let's get rid of z in the other equations, right? So again, let's start off by numbering them. So we have the first one, the second one, and the third one. So we want to get rid of z. This one has negative z and 3z. So let's multiply number 1 by 3. So our second version of 1, basically, is 12x plus 6y minus 3z is equal to 33. Right? So now we're going to take 1 and 3, so that's 12x plus 6y minus 3z is equal to 33, and 2x minus y plus 3z is equal to 18. So let's add these together. 12x and 2x is 14x. Then 6y and minus y is plus 5y. Negative 3z is plus 0z. And then 33 and 18, that's 51. So now we have our fourth equation, which is 14x plus 5y is equal to 51. And remember, equation 2 is x plus 3y equals 1. So that means which variable do we want to get rid of next? Y's don't match up very well because we have 5 and 3. We'd have to multiply both equations by something. The x's do, though. We just have to multiply the second equation by negative 14. So our new version of 2 is negative 14x minus 3 times 14 is 2, put my 1 is 42, y equals negative 14. So what we're going to do now is 2 and 4, so that is negative 14x minus 42y is equal to negative 14, and 14x plus 5y is equal to 51. Add these together. So 14x and negative 14x make 0x. Negative 42 plus 5 is negative 37y is equal to negative 14 and 51, that's 37. So then our fifth equation in this one is negative 37y is equal to 37, which really gives us y is equal to negative 1. There's our first solution, right? So now let's go back to the very first version of 2 to plug in because it's nice and simple looking, right? So then we get x plus 3 times negative 1 equals 1. So x minus 3 is equal to 1. So x is equal to, let's see, add the 3, so we get x is 4. So there's our second, right? So now we have to go back into either 1 or 3 because we can't use 2. So 1 or 3. So we want to find z. Let's use the first one because z is on its own at least. So we have 4x, which is 4, plus 2y, which is negative 1, minus z is equal to 11. So we have 4 and 4 is 16, minus 2 minus z is equal to 11. So that's 14 minus z equals 11. I'm just going to add the z and subtract the 11. So z is equal to 3. There's our third solution, right? So that means our ordered triple is 4, -1, and 3. And that's our solution. Again, we can plug in. Now, the nice thing about this one is we used this equation to find x, so it's going to work. We used this equation to find z, so it's going to work. So we just have to try it into the third equation, the only one we haven't used yet. So let's go ahead and make sure that it works in that one as well. After I can erase everything. Okay, so third equation, we have 2 times x, which is 4, minus y, which is -1, plus 3z, which is 3. So 2 and 4 is 8, minus -1 is +1, plus 3 and 3 is 9. So that's 8 and 1 is 9, plus 9 is 18. That is the solution, right? Okay, now, next. This one, as you can see, has possibilities. This is not necessarily one that will give us a unique solution, okay? We have to figure out kind of what this looks like first. So, let's go through same kind of steps, right? Number your equations. So we have 1, 2, and 3. Then, what do we have going on here? Let's look at our variables first. Which one kind of is easy to get rid of first? Well, I'd say x's are pretty good because first equation has x, second has -x, and third has -2x. That's pretty simple to get rid of x's. So the very first one we're going to do is 1 and 2. So that's x plus 2y minus z is equal to -3, and -x plus y plus 2z is equal to 5. So that is 0x plus 3y plus z is equal to 2. So then our fourth equation is 3y plus z is equal to 2. Then we want to get rid of the x in the third equation now. That means number 1 needs a 2 in front of the x. So let's multiply him by 2, and we get a new version, which is 2x plus 4y minus 2z is equal to -6. So the next thing we'll do is kind of the new version of 1 and 3 together. So that is 2x plus 4y minus 2z is equal to -6, and -2x plus 5y plus 5z is equal to 12. So then add them together. So we get 0x plus 9y, let's see then, plus 3z is equal to 6. So our fifth equation then is 9y plus 3z equals 6. Now, one thing I want to point out right now is that every single one of these terms is divisible by 3. Go ahead and do that to have the simplest version that you can working with for right now. So divide by 3. That means we get 3y plus z is equal to 2. Oh wait, our number 5 equation is the exact same thing as our number 4 equation. What does that mean? Well, when we get this, when we try to start eliminating equations, and we have the fact that we just kind of got 2 of the same thing, right? Well, that just means that we'd get something like a true statement. Because if we multiply this number 5 by negative 1. We would get negative 3y minus z is equal to negative 2. Then if we did 4 and 5, we would have 3y plus z is equal to 2, and negative 3y minus z is equal to negative 2. Well, if we add those together, we get 0 equals 0. I hope 0 always equals 0, right? So that means this is just a true statement, always. That means this is infinitely many solutions, okay? So now, we take that as kind of this option right here, okay? So that's the one that we're going to kind of go from. You can technically choose any single one of these, okay? There's kind of sometimes a nicer one at times, but they will all kind of truly work for us. All right, so if we look at this, let's think here. Normally what you want to look for is an variable that kind of goes through in multiple of your equations here. So let's see. Well, we have z and y in both of these equations. So we could choose either one of those, technically, right? And then we could also kind of actually choose the x, but because it's not in either of these equations, we probably don't want to. Sometimes it's just as easy, okay? It doesn't truly kind of matter necessarily. So what we're actually going to do then is, I'm gonna make some space here, is I'm going to do another elimination and get rid of a different variable. Okay, so we got rid of x's before. Let's choose another one that's easy to get rid of. So if we look at 1 and 2, well, their z's look like they're pretty easy to get rid of. As long as we multiply, which we already did, right here, right? And got this equation. If we take this 1 and 2 and add them together. So 1 and 2, we already kind of did that, but we're using the kind of changed one, right? So we have 2x plus 4y minus 2z is equal to negative 6, and we have negative x plus y plus 2z is equal to 5. Let's add those together. So we get x plus 5y, no z's, is equal to negative 1. So now we have an equation with x and y, and we have an equation of z and y. So that means we have y being the consistent variable between them, right? So we're actually going to choose the y version right here. What that means then is you solve for the other variable in terms of y. So from this equation right here, I'm going to solve for x. So that means x is equal to negative 5y minus 1. And then I'm going to solve this equation for z. So then z is equal to negative 3y plus 2, right? So now what our solution order triple looks like is x, which is in terms of y, negative 5y minus 1, y, and then what z is in terms of y, which is negative 3y plus 2. That is our kind of ordered triple now. It's always putting all three variables in terms of one of them. You get to choose which one, okay? So these are kind of sometimes the hardest ones because you have to figure out kind of which one to choose. But it truly does not matter, okay? I could have chosen z just as easily, except then I would have needed to get rid of y, which we could have done as well, okay? All right, now, so let's go on to the last example here. So this is a word problem. It's Salma, John, and Chow have a total of $99 in their wallets. Okay, so let's set this up. We already have that first sentence. We have some knowledge that we can do, right? So Salma, let's call her S, and John J, and Chow C. So have a total of $99 in their wallets. So that means their wallet amounts get added together, right? To create that equation. Now, Chow has $7 less than Salma. Okay, so Chow is less than Salma. That's how we want to think about it. C is less than S. So that means if we want to set them equal to each other, we need to add something on to Chow or take away something from Salma, right? So Salma is equal to Chow plus 7. Okay? Now, John has 2 times what Chow has. So again, John is more than Chow's amount, right? 2 times as much. So that means if we want them equal, we need to make John smaller or Chow's bigger, right? So John is equal to Chow times 2, because it's 2 times as much. So now, how much do they have in their wallets? Well, because of how we set this up, we have S in terms of C and J in terms of C. We can replace right here and have one equation with only C. So S is C plus 7 plus J, which is 2C, plus C is equal to 99. So combine like terms, we have C, 2C, and C again, so that's 4C plus 7 is equal to 99. So 4C is equal to 92. If we divide, well, dividing by 2 gives us 46 over 2, so then divide again, that is 23. So Chow has 23. That's not our answer. That's just Chow, right? We also want to find how much Salma and John has. So we can use these 2 equations. It's already in terms of C, right? So Salma then has Chow plus 7, right? So 23 plus 7 is 30. So that's how much Salma has. Then John is 2 times Chow, which is 23. So 2 times 23 is 46. That's the third one. So that means we have what then? We have, if we put it in S, J, C format for an order triple, that means we have 30, 46, and 23. Okay? So that is section 8.2.